This lesson looks at different methods for solving inequalities. Some of them are not much different from solving equations, but as they get more complicated, you'll see the techniques that you may have learned for solving equations you cannot apply when working with inequalities. So we'll start with some fairly straightforward examples. Here's a linear equation, and you can solve it by subtracting 3 from each side and then dividing each side by 2. This equation has one solution, x equals 7, and it can be shown on a number line as a single point with a value of 7. If we replace the equal sign with an inequality, we can perform the same operations. This is saying that we can take any value of x which is greater than or equal to 7, and we show that on the number line by marking the number 7 and placing an arrow on the line showing that any value greater than or equal to 7 fits this original inequality. In the third example, we'll gather our x's onto one side and our numerical constants on the other. If we subtract 7x from both sides and add 9 to both sides, now we have an example where you can't just divide both sides as you would if it was an equation. If we did that, we would be saying that x is greater than or equal to -5. So if we took, for example, a value of 1, because that is greater than -5, 5 take 9 is -4, and 1 plus 7 is 8, but clearly -4 is not greater than or equal to 8. So most people try and remember that when dividing by a negative number, you need to reverse the inequality. From the original equation, if we instead subtract 5x from both sides and subtract 1 from both sides, now we can divide by 2. -5 greater than or equal to x is the same as x is less than or equal to -5. On a number line, if we take any value of x which is less than or equal to -5, multiply that value by 5 and subtract 9, it will always be greater than or equal to multiplying that number by 7 and adding 1. Now, strictly speaking, we should write our solution using set notation. So notice the curly brackets. X is an element of the set of real numbers such that x is less than or equal to -5. In example number 4, we have a quadratic inequality. Just as when we're solving a quadratic equation, we start by seeing if we can factorise. Now, the reason for factorising a quadratic equation is because when two factors multiply to give 0, this means that one of the factors must be 0. Now, what if instead of being equal to 0, our product of factors is greater than or equal to 0? In other words, our expression is positive. Well, if two factors multiply and the result is positive, then there are two possibilities. Either both of the original expressions are positive, or both of the original expressions are negative. And of course, if either of these factors is 0, then the inequality holds true because we're working with greater than or equal to 0. So we'll test out both of these possibilities. Firstly, both of the factors are positive. X must be greater than or equal to 5, and x must be greater than or equal to -3. Any number which is greater than or equal to 5 is also going to be greater than or equal to -3. And so this is our first solution. So our second possibility is that both factors are negative. But any value of x which is less than or equal to -3 is also going to be less than or equal to 5. So we've found our two solutions to the original inequality. The graph of y equals x squared take 2x take 15 is a parabola. It has a positive coefficient of x squared, and so it has a minimum turning point. It has roots at -3 and 5, and the values for which this function is greater than or equal to 0 are when x is less than or equal to -3 and when x is greater than or equal to 5. And you should also check the capabilities of your calculator to make sure that you can solve inequalities and get the solutions required. Example number 5 consists of a quotient which is greater than 0. We can apply a similar principle to the previous example. If we have the quotient of two expressions being positive, then there are two possibilities. Either both the numerator and the denominator are positive, or both the numerator and the denominator are negative. So we'll test out these two possibilities. If the numerator and the denominator are positive, this means that x is greater than 0 and x is greater than 3. Now, values of x which are less than 0 or between 0 and 3 do not satisfy both of the inequalities, but any value of x which is greater than 3 is also going to be greater than 0. And so we have a solution. Any value of x which is greater than 3 will result in x over x take 3 being greater than 0. Our second possibility is that both numerator and denominator are negative, which means that x is less than 0 and x is less than 3. So this time, any value of x which is less than 0 is also going to be less than 3. Now we've found our two solutions to the original inequality. Another possible approach is to look at the original quotient, and you can see that the key values here are when x is 0 and when x is 3. Clearly x cannot be equal to 3, or we would be dividing by 0. So we can check possible values of x which are less than 0, between 0 and 3, and greater than 3. For example, when x is 4, 4 over 1 is greater than 0. When x is negative 1 is also greater than 0. But when x is 1, 1 over negative 2 is not greater than 0. So any values between 0 and 3 do not satisfy the original inequality. And notice that I've used open circles on the number line to show that x cannot equal 0 and x cannot equal 3. If x was 0, then this quotient would be equal to 0 and not greater than 0. And if x was 3, then we would have the situation where we're dividing by 0. If we plot the graph of y equals x over x take 3, it looks like this. And you can see that the values of x when the function is greater than 0 are anything where x is less than 0, and also we actually have an asymptote here. Values of x to the right of that asymptote also result in positive values of the function. And again, you should check that you are able to solve an inequality such as this using your class pad to get the two possible solutions. Example number 6 is another quotient, and this time the quotient is negative. If a over b is negative, that means that either a is negative and b is positive, or a is positive and b is negative. Firstly, if x squared take 16 is negative and x take 3 is positive. Now x squared take 16 is a quadratic. If we were to graph that quadratic, it would look like this. It has a turning point at 0, negative 16. And for what values of x is the function negative? Well, if we factorise, the two roots of this quadratic are 4 and negative 4. The function is negative between negative 4 and positive 4. The solution for this part is when x is between negative 4 and positive 4. But at the same time, x must be greater than 3. Combining these two together gives the solution that 3 is less than x, which is less than 4. The second possibility is that x squared take 16 is positive and x take 3 is negative. X squared take 16 is positive. That's when x is less than negative 4 or x is greater than 4. But at the same time, x must be less than 3. X cannot be greater than 4 and less than 3. So this one is not possible. So now we have our two solutions, and writing our answer in full, we could say that it is the union of two sets of real numbers, the first set being all the possible values when x is less than negative 4, and the second set all the possible values of x between 3 and 4, exclusive. In example number 7, you might be tempted to think of this as an equation. If this were an equation, you might start by multiplying both sides by the denominator and then expanding and gathering all the terms on the left-hand side, factorising and using the null factor law. However, what you cannot do is simply replace these equal signs with inequalities. The reason being, if the denominator is negative and we multiply both sides by a negative value, that then reverses the inequality. A more reliable approach is to try and arrange the inequality in the form a over b inequality 0, and then we can consider positive and negative values. So I'll start by subtracting x plus 15 over x plus 3 from both sides. And because I want to combine these terms into a single fraction, I'm going to multiply x by x plus 3 over x plus 3. So my common denominator is x plus 3, and if I expand and combine the numerators and then factorise, I now have the inequality in a form which enables me to use this quotient method. So if the quotient is less than or equal to 0, I have two possibilities. Firstly, the numerator is less than or equal to 0, and the denominator is greater than 0. Now notice that the denominator cannot be equal to 0. The second alternative is that the numerator is greater than or equal to 0, and the denominator is less than 0. So the first part of the first possibility consists of a quadratic with roots at -5 and 3, and we want to know the values of x when this function is less than or equal to 0. So that's when x is between -5 and 3 inclusive. And this is combined with values of x which are greater than -3. So to put these two inequalities together, -5 less than or equal to x less than or equal to 3 is represented by this red line here, and x greater than -3 is represented by the blue arrow. And because our solution requires that both of these inequalities hold, our first solution is -3 less than x less than or equal to 3. The second possibility is when x plus 5, x take 3 is greater than or equal to 0, and x plus 3 is less than 0. So in the first part, we require x values that result in a positive value of this quadratic function. So that's when x is less than or equal to -5 or greater than or equal to 3. And that needs to be combined with x less than -3. Now it's impossible for x to be greater than or equal to 3 and at the same time be less than -3. So we can discount this option. And then for x to be less than or equal to -5 and at the same time less than -3, we can see that any values of x less than or equal to -5 satisfy both inequalities. And so our final solution to this inequality is that x can be any value between -3 and 3, including +3 but not including -3, or x can take any value less than or equal to -5.